Good day to all of you. So we're already finished with file system interface. So now in this chapter, we have the file system implementation. So how does the file system is implemented in different operating systems? So to know more about this, so let's start our lesson. So again, chapter 14 is all about file system implementation. So the contents of chapter 14 are file system structure, file system operations, directory implementation, allocation methods, free space management, efficiency and performance, recovery, and then we have an example of a WAFL file system. So the objectives of this chapter are describe the details of implementing local file systems and directory structures, discuss block allocation and free block algorithms and trade-offs, explore file system efficiency and performance issues, look at recovery from file system failures, and describe the WAFL file system as a concrete example. So first is we have the file system structure. So the file structure, it is considered to be a logical storage unit, and it is a collection of related information. Again, as I've already cited as an example in the last chapter, if you have a file, a very large video file, so we can see that as one file in our folder, but in reality, in the hard drive, there is a possibility that this large video file, it is stored in a non-contiguous fashion. So the chunks of its parts of its file are scattered in the disk. And then file system resides on secondary storage or disks. So file system provided user interface to storage, mapping logical to physical, provides efficient and convenient access to disk by allowing data to be stored, located, retrieved easily. So that is the function of file system. For us users, actually we do not care how does our file is stored, as long as if we save that file in our hard drive, we already seen that it is already saved. But how it is implemented and how it is saved, actually it's not our concern. And then disk provides in-place rewrite and random access. So I/O transfers performed in blocks of sectors, usually 512 bytes. And then we have this file control block, or FCB. This is a storage structure consisting of information about the file, and device driver controls the physical device, as we have already seen in the previous chapter, and file system organized in two layers. So this is the layered file system. So we have application programs, and then under that is we have the logical file system, and the next is the file organization module, and then we have the basic file system, I/O control, and devices. We as user, we are only with communication with the application programs. Actually, we don't care about the logical file system, file organization module, basic file system, and the I/O control. It's like that they are already working in background. All we have to worry about is our application programs, how we interact and how we use the application programs installed in the computer. So we have a further discussion of those layers. So for the file system layers, so device drivers manage I/O devices at the I/O control layer. So given commands like that device driver, like read drive 1, cylinder 72, track 2, sector 10 into memory location 1060. Outputs low-level hardware-specific commands to hardware controller. And then the next layer is we have the basic file system, given command like retrieve block 123 translates to device driver. And basic file system also manages memory buffers and caches, such as allocation, freeing, and replacement. So buffers hold data in transit, and caches hold frequently used data. And then next layer is the file organization module, understands files, logical address, and physical blocks. It translates logical block number to physical block number, and it also manages free space and disk allocation. And then the next layer is we have the logical file system just under the application program. It manages metadata information. It translates file name into file number, file handle, location by maintaining file control blocks or inodes in Unix. And it is also responsible for directory management and protection. So layering useful for reducing complexity and redundancy, as I've said. All we have to do as user is to save our files, retrieve it, open it. We do not care how does the operating system and the file system is doing that, but adds overhead and can decrease performance. So for this one, logical layers can be implemented by any coding method according to OS designer. So next is we have many file systems, sometimes many within an operating system. So it's not only the file system that is used in the hard drive, there are also file systems that exist that is also used in the whole computer system, such as this one. So each with its own format. For CD-ROM is ISO 9660. So Unix has UFS. So Unix is, of course, UFS is Unix file system. And then it also uses also the FFS or the Berkeley Fast File System. So Windows has FAT or FAT. FAT means File Allocation Table. So we have FAT32 meaning it's 32-bit. And then we have NTFS. So NTFS means New Technology File System, as well as Flappy. Flappy has its own file system, but of course, we're not using that anymore. And then again, for CD, DVD, Blu-ray, and then also Linux has more than 130 file system types with extended file system ext3 and ext4 leading. So actually ext3 and ext4, these are the file system that is used by Linux for the disk, while for Windows it uses actually nowadays it already uses NTFS. FAT32 and FAT is used for older um, versions of Windows. And then Linux also has using file system for distributed file systems. And then new ones still arriving, such as ZFS. So ZFS means zettabyte file system. And then of course Google FS. So particularly this is a file system used by Google. And then we have the Oracle ASM. So ASM stands for Automatic Storage Management. And we also have FUSE or FUSE. It stands for File System in User Face. So this provides flexibility in file system development and used by implementing and executing file system as user level rather than kernel level code. So these are the newer technologies in terms of file system. And then next is we have file system operations. So we have system calls at the API level, but how do we implement their functions? So the answer to that is on disk and in memory structures. So we have the boot control block contains information needed by the system to boot OS from that volume. So of course, all of the operating systems or all of the computer system with operating systems installed have this boot control block. It is impossible that your computer will not have that, because if you do not have that boot control block, how does your computer, every time that you're going to open your computer or power up your computer, that it will load your operating system? So the boot control block is needed if volume contains OS, usually the first block of volume. Okay, we also have the volume control block or super block, which is called in UFS, and master file table if it is in NTFS, specifically in Windows. This contains volume details such as total number of blocks, number of free blocks, block size, free block pointers or array. And then we have directory structure, organizes the files. So as you can see with the previous chapter, that directory contains folders, and then of course there are files inside. And then names and inode numbers, and then master file table. So next is we have for per file control block or FCB contains many details about the file, typically inode number, permission, size, and dates. And then for MTFS, stores into master file table using relational DB structures. So we can already see this if you've seen the last chapter. So just right click the file and then click on properties, and then of course you can see there's the file permission, the file dates when it was created and access, and then write, and then who is the file owner, group, and ACL, then the file size, and file data blocks or pointers to file data blocks. Okay, next is we have the in-memory file system structures. So mount table storing file system mounts, mount points, and file system types. So mount table, as I've said in the last chapter, that disks need to be mounted so that you can access it. So also our flash drives, if you're going to connect it into our computer, it is automatically mounted. Actually, all of our disks also, once that it is the operating system has already loaded, it will also be automatically mounted. So for you, there's no hassle for the user to manually mount the drives. And then next is we have the system-wide open file table contains a copy of the FCB of each file and other info. And then we also have the per process open file table contains pointers to appropriate entries in system-wide open file table as well as other information. So the following figure illustrates the necessary file system structures provided by operating system. So for letter A refers to opening a file, and then for letter B refers to reading a file in the next slide. And then plus buffers hold data blocks from secondary storage. So for opening a file, returns a file handle for subsequent use. And then data from read eventually copied to specified user process memory address. So this is an illustration for this letter A is for opening a file and this is for reading a file. For example, if you're going to open a file, okay, you're going to click the icon of that particular file. So what happens here is that it will the system call will go to the kernel memory, and then it's going to access the directory structure where the file name is located, and then next is it will from the file control block, of course, the details about the file, and this is the file for that, the contents for that file, and then it will be sent back to the kernel memory. And then, of course, as it is said, that opening returns a file handle for subsequent use because the user has opened the file. And then next is we have the reading a file. So if a user will read a file, so it needs two table, the per process open file table. Then you just need the index because for per process open file table, it just needs an index identification, and then it will be it is point it will it points to the system wide open file table, and then we have the data blocks, and of course again it needs the file control block. So the difference between the two is for opening a file, it only just needs directory structure in kernel memory, while for reading a file, it needs per process open file table and system wide open file table, which is also located in kernel memory. Okay, next is we have directory implementation. So linear list of file names with pointer to the data blocks. So linear, so it's very simple to program, but it is time consuming to execute. And then for search time its search time is linear, and then could keep ordered alphabetically via linked list or use B plus 3. And then another directory implementation is by means of hash table, linear list with hash data structure. So this decreases directory search times. But the problem with hash table is that there is a possibility of collisions. So collisions are situations where two file names hash to the same location. So to avoid that, so only good if entries are fixed size or use chained overflow method. So next is we have, or this topic, we have the allocation methods. First is contiguous. So the term contiguous means that you're going to store the parts of the file adjacent to each other. So an allocation method refers to how disk blocks are allocated for files. So specifically for contiguous allocation, each file occupies set of contiguous blocks. So it is best performance in most cases, and it's also simple. What you only need the starting location or the block number and length or number of blocks that is required. And then problems include finding space for file. What if, for example, the file exceeds the free space blocks that is needed? And then also knowing the file size, and then it also has external fragmentation. So external fragmentation, I've already discussed it in the previous chapters. And then contiguous allocation, need for compaction offline, or if the computer is downtime, or online. So compaction, an example of compaction is defragmentation, so in case of disk drives. So this is an example, an illustration for contiguous allocation. So mapping from logical to physical. For example, logical address, of course, it is said that the capacity of each blocks is 512 bytes. And then we have the QNR. So block to be accessed is equal to Q plus starting address. So, and then displacement into block is equal to R. So, to further understand this Q and R, we have an example here. So, for example, in the directory, so we have file count. So, the starting block is in 0. So, as you can see, this is count. And then we have 0. And then length is 2. So, it only needs 2 blocks. So, we have 1, 2. So, it occupies 0 and 1. And then for file TR, so file TR, it is located on block 14. So this is TR block 14, and it requires 3 blocks. So that's why 1, 2, 3, 14, 15, and 16 is occupied by file TR. And then mail, the starting block is 19, and it needs 6. So that's why 1, 2, 3, 4, 5, 6, from 19 to 24 is occupied by file mail. And then next is we have list. List starting block is 28, and it needs for 1, 2, 3, 4. So 28 to 31 is occupied by file list. And last but not the least is we have F. So starting block is 6, and it only needs 2 blocks. So 6 and 7 is occupied by file F. So that is that example of contiguous allocation. So the blocks that it will use are adjacent with each other. So that's why I told you contiguous means adjacent. Okay, next is we have the extent-based systems. So many newer file systems, such as the Veritas file system, use a modified contiguous allocation scheme. And then extent-based file systems allocate disk blocks in extents. So an extent is a contiguous block of disks. So extents are allocated for file allocation, of course, and a file consists of one or more extents. So next is, aside from contiguous allocation, is we have the linked allocation method. So linked allocation, each file a linked list of blocks. So file ends at nil pointer. There is no external fragmentation. And then each block contains pointer to next block. And then there is no compaction. And as mentioned, no external fragmentation. Free space management system called when new block needed. Improve efficiency by clustering blocks into groups but increases internal fragmentation. And reliability can be a problem because, of course, each block contains pointer to next block. And locating a block can take as many IOs and disk 6. So that it's disadvantage. Okay, so an example of a linked allocation method is the FAT, or the file allocation table variation. So beginning of volume has a table indexed by block number, much like a linked list, but faster on disk and cacheable. And the new block allocation is simple. So for linked allocation, so each file is a linked list of disk blocks. Blocks may be scattered anywhere on the disk. So the block, it always has a pointer here and the mapping for the logical address by 511 bytes. And then we also have the QNR. Block to be accessed is the Q block in the linked chain of blocks representing the file, and displacement into block is equal to R plus 1. So to further understand that is we have this illustration. So we have the file zip, okay, and then we have the start block which is 9, and this block has a pointer to the next block and the succeeding blocks. As long as, of course, the end is, it will end on block 25. So, for example, we have block 9, and then it points to block 16, and block 16 points to block 1, and then block 1 points to block 11, and then block 11 points to block 25. So, that is the end. So that is the mechanism of linked allocation. Every block has a pointer to the next block. So it does not matter if they are not contiguous as long as they have pointers to the next block. So this is the file allocation table similar to the link allocation. So for this one, so the name of file is test, and then the start block is 217. So we have 217 here, and then also there is a pointer going to the next block which is 618. So it will go to 618, and then it will the pointer is pointing next to 339, so it will point to 339. So this is FAT is similar with linked allocation. Okay, next is we have the next allocation method, which is the indexed allocation. So each file has its own index blocks of pointers to its data blocks. And then the logical view is we have an index table and it points to a number of blocks. So this is an example or an illustration of index allocation. So again, we have file zip, and then the index block is 19. And inside this block 19 contains the blocks that will be used by the file. And then we have -1 here, meaning that these are empty. Only, so allocated here is 1, 2, 3, 4, 5, 6, 7, 8, but only 5 blocks are used. So for block 19, it will point, of course, to 9, then we have 16, and then we have 1, and then we have 10, and then we have 25. So that is the indexed allocation. So combined scheme for Unix UFS or the Unix file system, we have 4 kilobytes per block and then 32-bit addresses. So this is the allocation method. So for this one, we have the file metadata and then direct blocks, meaning it points to actually to the data, and then while the single indirect blocks, they have an index and then it will point to the data. For double indirect blocks, it uses 2 index tables and then 2 levels of index tables, and then it will point to the data. And of course, the triple indirect blocks, so it uses 3 levels of index tables before it will be accessing the actual data. So more index blocks that can be addressed with 32-bit file pointer. So performance, which of them is the best? So best method depends on file access type. So contiguous is great for sequential and random. And then linked allocation is good for sequential but not random accessing method. And then declare access type at creation, select either contiguous or linked. And then index actually is more complex. So single block access could require 2 index block reads, then data block read. And then clustering can help improve throughput, reduce CPU overhead. So for NVM or non-volatile memory, no disk head, so different algorithms and optimizations are needed. So using old algorithm uses many CPU cycles trying to avoid non-existing head movement. And then when with NVM goal is to reduce CPU cycles and overall path needed for I/O. Okay, next is we have the free space management. So file system maintains free space list to track available blocks or clusters. So we're going to use term block for simplicity. So for free space management, so the free space list can be a bit vector or bitmap, which is composed of n blocks. So this is the free space list for bit, and then it's an array. I is equal to, so if it is 1, block I is free, meaning it's empty. And then if it is 0, block is occupied. So block number calculation is number of bits per word times number of zero value words plus offset of first 1 bit. So CPUs have instructions to return offset within word of first 1 bit. So bitmap requires an extra space. So we have an example here of a calculation. So block size is 4 kilobytes is equals to 2 raised to 12 bytes. And the disk size is 2 raised to 40 bytes or 1 terabyte. So n is equal to 2 raised to 40 divided by 2 raised to 12 is equals to 2 raised to 28 bits or approximately 32 megabytes. So since our block size here is 4 kilobytes, so if clusters of 4 blocks, we have to divide it by 32 divided by 4. So we have 8 megabytes of memory. So for bitmap, it is easy to get contiguous files. So we have a linked free space list on disk. So it can also be done by using a linked list. So of course, these are the free list. Cannot get contiguous space easily. Of course, there are, as I've said, for a file, sometimes it is stored in contiguous fashion, but sometimes it is scattered uh, around the disk. So for this implementation, there is no waste of space and no need to traverse the entire list if the number of free blocks are recorded. For example, for linked list, so this is the free space list head starting with 2 and then 2 points to 3, then 3 points to 4, 5, 8, 9, 10, so on and so forth. So that is the linked free space list on disk. Just like with linked allocation, it's just that for this example, of course, linked list is used for free space list. Okay, next is we can also do the grouping. So modify linked list to store address of next n minus 1 free blocks in first free block plus a pointer to next block that contains free block pointers. So we can also do the counting because space is frequently contiguously used and freed with contiguous allocation, extents or clustering. So keep address of first free block and count of following free blocks. And then the free space list then has entries containing addresses and counts. So it can also be implemented by using space maps. So it is used in ZFS. So consider metadata I/O on very large file systems. So full data structures like bitmaps couldn't fit in memories because of thousands of I/Os. So divides device space into metaslab units and manages metaslab. So what is metaslab? These are chunks of blocks. So this is used actually in ZFS. So in ZFS, a pool of storage is split into metaslabs for easier management for easier management of the free space. And then this metaslab, so given volume can contain hundreds of metaslabs. And then each metaslab has associated space map. So to have this associated space map, it uses counting algorithm. So this algorithm is to store information about free blocks. So but records to log file rather than file system. So log of all block activity in time order or in counting format. And then the metaslab activity loads space map into memory in balanced tree structure indexed by offset. So replay log into that structure and combine contiguous free blocks into single entry. Next is we have trimming unused blocks. So hard disk drives overwrite in place, so need only free list. So blocks not treated specially when freed, so keeps it data but without any file pointers to it until overwritten. So the question now is, if I'm going to ask you, what happens when you delete a file, not just deleting it, but deleting it in the recycle bin? Actually, what happens is, actually, the answer is already in here. All of your files in your computer, that's why you can access it, because they still have this so-called file pointers. Once you delete it, not just deleting it just right click and delete. No, because you can still retrieve that on the recycle bin. But once you deleted it in the recycle bin, the file actually the file is still there, but what you are deleting are or is the file pointers for that file. If you do not have any file pointers for that file, you cannot access it. Just imagine the analogy for that is, for example, you have a wall. If your wall is a bare wall, no paint, no, there's no paint, and then, for example, you're going to format it. Format it is, for example, you're going to paint the wall. Okay, you're going to paint. Example, your favorite color is light blue. And then years later, you became bored with your blue wall, and then you want to change the color. So what are you going to do? Are you going to remove the paint for the blue wall and make it bare again, which is very impractical? So what are the persons doing, or what are others are doing? Instead of removing that color blue wall, you're just going to apply a primer, and then add if you want, for example, a green color for your wall, you're just going to repaint it without removing the color blue paint underneath. So it's just like that. Okay? So I don't know if you still remember. I know it's a gossip, it's a celebrity gossip or show business gossip. If you can remember that there is a news that a male celebrity sold his laptop, and then um, and he made sure that he formatted the disk of that laptop clean. There's no file inside, only the operating system. But he was very surprised that someone uploaded his video crying that her then girlfriend has he's crying because her then celebrity girlfriend has aborted their unborn child. If you can remember that. Okay, not let's not focus on the gossip, but the question is, how did that video came to surface? Because as he said, he made sure that when he sold his laptop, there are no files. There are already no files. He already formatted it. So that is already an evidence that you can really recover your files. Your files are still there. The one who uploaded, he or what whoever she is or he is, he has he or she has that tool to recover those files, even though the drive is already being formatted. Okay? So actually there are tools to use that. So I have this one. So it's called Recuva. So let's have this an illustration. So that's what I've been telling you with even though you formatted your drive, as long as it's still intact, it's still there. Okay. The Recuva, this is a free software that you can download. Actually, this is very helpful for me because there are people, for example, their flash drives, they accidentally formatted it, or a memory card, they accidentally deleted the files. I always advise them that if you accidentally deleted the file, do not um, do not make any changes there. For example, if you've deleted it accidentally, so that if you're going to recover the file, it will be the files are still intact. So actually, recovers are really a great help for recovering files. Okay, this is the options for general. So okay, this is the recovering. So you can see one pass. It's like as I've told you, um, deleting will only the file is still there, and then if you're going, then it's already considered a free space, and then what will happen is that the operating system will overwrite. It's not really overwrite, um, but will it's under and the older files are underneath. So as you can see here, simple overpass. It's just you're going to recover the file um, underneath one layer. As you can see, one pass, and then the another is three passes, meaning you're going to drill down the contents of the old files that is buried under. So it's like three layers under, and then seven layers under, and then this is of course 35 passes. So it will really take long for you to recover those files. So 30, it's like you imagine 35 layers. It's like that. Of course, this is the most effective because you can really recover your old files. So this is the Recuva. Okay. Is there a possibility that your you can delete the files that is it's like buried? Of course there is. So there is another program which is actually CC Cleaner. So let's open it. Okay, then we have these options also. Actually, the makers of Recuba and CC Cleaner are one company. So for options, and then we have this. Okay. Okay. I'm not really using this. Okay, Drive Wiper. So Drive Wiper, what does this do? Drive Wiper is it deletes the buried old files. Okay? So you can see 1 pass, 3 pass, 7 pass, and 35 passes, just the same with Recuva. So it means, of course, very complex overwrite. So that means drive wipe, it will really um, um, delete your old files underneath the current file. Actually, I haven't used this one because I have nothing. For me, I have nothing to hide. So that's why maybe you can use this, for example, if you're going to sell your laptops and of course you have top secret files that you want to of course to be deleted and not to be accessed anymore. So you can use this drive wiper. Okay. So again, what you've learned now is that if you formatted your storage devices, it does not necessarily mean that the files are gone. They're only there. The only lost is the so-called file pointers. Okay. So actually, I do have already an idea when that gossip of that male celebrity that it really is not gone. It's just listed as free space, but that your old files are still there, and then it will be overwritten. It's like, again, the analogy is like repainting the wall many times. And if you really want to uncover for example, the color of your wall, the original color of your wall, of course, you can remove the paint, the to see the underlying paint. So that's my analogy for that. Okay, next, let's continue. So storage devices not allowing overwrite like NVM. So this overwrite, they suffer badly with same algorithm. So must be erased before written. Erases made in large chunks or blocks composed of pages and are slow. And then trim is a newer mechanism for the file system to inform the NVM storage device that a page is free. Can be garbage collected, or if block is free, now block can be erased. As you can remember, for NVM or non-volatile memory, you cannot overwrite a block unless you erase the contents. But for hard disk drives, they're only deleting the file pointers and then list that block as free, and then hard drives can overwrite the files. They're only buried under. Okay, next is we have efficiency and performance. So efficiency dependent on disk allocation and directory algorithms, types of data kept in files directory entry, pre-allocation or as needed allocation of metadata structures. It can be fixed size or varying size data structures. So for performance is keeping data and metadata close together. And then we have the buffer cache, separate section of main memory for frequently used blocks. And then we have the synchronous writes, sometimes requested by apps or needed by OS. So what is synchronous write? This occurs in the order in which the storage subsystem receives them, and the writes are not buffered. So, of course, it is indicated that writes are not buffer, so there is no buffering or caching. Writes, writes must hit disk before acknowledgement. And then we also have asynchronous writes, which is more common, bufferable and faster because synchronous follows a certain time interval while asynchronous writes are not. So, asynchronous write, the data are stored in the cache and control returns to the caller. So other techniques are free behind and read ahead. These are techniques to optimize sequential access. So free behind is sequential I/O performance optimization that removes a page or block from a buffer as soon as I/O to the next page is requested. So that is the free behind. And then we have the read ahead. It's also a sequential I/O performance optimization that reads and caches several subsequent pages when a read of one page is requested. So reads frequently slower than writes. Okay, next is we have the page cache. So a page cache caches pages rather than disk blocks using virtual memory techniques and addresses. So also memory mapped I/O uses a page cache, and routine I/O through the file system uses the buffer or disk cache. So this leads to the following figure. So we have an illustration of I/O without a unified buffer cache. So with this illustration, do we can are we facing a problem here? Actually, so the read, for example, you're going to read read and write system calls go through the buffer cache. So this is the buffer cache. The memory mapping call, however, requires using two caches, the page cache and the buffer cache. So the memory mapping call, which is used by memory mapped I/O. It uses the page cache and buffer cache. So a memory mapping proceeds by reading in disk blocks from the file system and storing them in the buffer cache. So because the virtual memory, as you can remember, it only uses page cache and it does not have any access with buffer cache. So what happens here is that the contents of the file in the buffer cache must be copied into the page cache. So what happens here is double effort. So this situation known as double caching requires caching file system data twice. So you already have a file copy here in the buffer cache, but since virtual memory is accessing the page cache and not the buffer cache, you have to copy it also in the page cache. So that is the so-called double caching. So the problem is that, of course, it's a double effort. So not only does this waste memory, but it also wastes significant CPU and I/O cycles due to extra data movement within system memory. So to solve that is we have this term unified buffer cache. So unified buffer cache uses the same page cache to cache both memory map pages and ordinary file system I/O to avoid double caching. So, but the question now here is, but which caches get priority and what replacement algorithms to use? So the answer to that is regardless of whether we are caching storage blocks or pages or both. Least recently used, or LRU, seems a reasonable general purpose algorithm for block or page replacement. So, modifying the illustration, so now the I/O is now using a unified buffer cache. So it means the memory mapped I/O and the I/O using the read and write system calls, they're already accessing the buffer cache. So that's why it's called unified buffer cache, because the original buffer cache and the page cache is already inside the buffer cache, and the virtual memory is already accessing this buffer cache. So there is no double caching that is happening in compare with the previous illustration. So next is we have recovery. So consistency checking compares data in directory structure with data blocks on disk and tries to fix inconsistency. So consistency checking can be slow and sometimes fail. So other types of recovery is use system programs to back up data from disk to another storage device. This storage device may be magnetic tape or other magnetic disk or optical, CD, DVD, or Blu-ray. And then you can also recover lost file or disk by restoring data from backup. So it's really very important to back up your data from different media. So the joke here is, for example, you have a thesis, your paper, and then you backed 5 versions in just one flash drive. So you have one backup. What if your backup, which is the flash drive, is also be corrupted? So where are you going to get your other copy? So an efficient backup is you should back up it in different media. So okay, next is we have the log structured file systems. So log structured or journaling file systems record each metadata update to the file system as a transaction. So all transactions are written to a log. So a transaction is considered committed once it is written to the log. So it is written in sequential fashion. So sometimes to a separate device or section of disk, and then however the file system may not yet be updated. So the transactions in the log are asynchronously written to the file system structures. So when the file system structures are modified, the transaction is removed from the log. If the file system crashes, all remaining transactions in the log must still be performed. So this is for a log structured file system. So faster recovery from crash removes chance of inconsistency of metadata. Okay, so on the last topic, we have an example, the WAFL file system. So it is used on network appliance filers and distributed file system appliances. So WAFL or WAFL is write anywhere file layout. So this serves up the NFS, CIFS, HTTP, and FTP. It is random IO optimized and write optimized. So the WAFL file system is also used by NVRAM for write caching. It is also similar to Berkeley fast file system with extensive modifications. So this is the WAFL file layout. So it has a root inode, and then an example, this block is pointing to an inode file, and then this inode file, it's an array. So there is for free block map and free inode map, and then we have blocks for file in the file system. So it can contain one or more file in the file system. So WAFL also do snapshots. So what is a snapshot? So this is an illustration. So before a snapshot, so your root inode has these pointers for block A up to E. And then we have letter B after a snapshot before any blocks change, meaning this snapshot, it saves the current state of WAFL. Okay? So this saves, so meaning it saves the root inodes pointers from block A to E. Okay. So what happens in C? There is a change in D. So now, because there's a change in D, the original D here, black D, will lose its pointer and the root inode will assign to the change D. So that's we have a D prime here. So after black D has changed to D prime. So this is the updated, meaning D here is already an old, it contains old files. So the root inode is now pointing to a change D. But our new snapshot still um, pointing to the old D. So what happens, for example, that the file, or there is a crash, or there is an error, there is a possibility that if you're going to recover, what you recover here is the saved snapshot, which is it will not show the changes in D. So for you to save the changes in D, you have to have another snapshot to save any changes in D. So that's what you call the snapshot. Okay, next is we have the Apple file system. So in 2017, Apple Incorporated released a new file system to replace its 30-year-old, very old actually, 30-year-old HFS Plus, or HFS meaning hierarchical file system. So HFS Plus had been stretched to add many features, but as usual, this process added complexity along with lines of code and made adding more features more difficult. Starting from scratch on a blank page allows a design to start with current technologies and methodologies and provide the exact set of features needed. So since HFS has already retired, so Apple has created their own file system, which is named Apple File System, or APFS. It is a good example of such a design. Its goal is to run on all current Apple devices, from the Apple Watch through the iPhone to the Mac computers. Creating a file system that works in watchOS, iOS, tvOS, and macOS is certainly a challenge, of course, because there are different devices. And then APFS is feature-rich, including 64-bit pointers, clones for files and directories, snapshot space sharing, fast directoryizing, atomic safe save primitives, copy on write design, encryption, it can be single and multi-key, and I/O coalescing. It understands NVMe as well as HDD storage. So most of these features we've discussed, but there are a few new concepts worth exploring. So space sharing is a ZFS like feature in which storage is available as one or more large free spaces or containers from which file systems can draw allocations, allowing APFS formatted volumes to grow and shrink. And then it also has fast directoryizing, provides quick use space calculation and updating. Atomic save is a primitive available via API, not a file system commands, that performs renames of files, bundles of files, and directories as single atomic operations. I/O coalescing is an optimization for NVMe devices in which several small writes are gathered together into a large write to optimize write performance. So Apple chose not to implement RAID as part of the new APFS, instead depending on the existing Apple RAID volume mechanism for software RAID. APFS is also compatible with HFS Plus, so it's backwards compatible, allowing easy conversion of for existing deployments. So that's the new file system by Apple. So we're already finished with chapter 14. So you already understand the file system implementation, the different allocation methods that is used, and we already understood that it does not necessarily mean that you deleted your file in the recycle bin that it will not be recovered. It will still be recovered with the right tools to use. So, if you do have any questions, so please feel free to comment below, and please don't forget to subscribe to my YouTube channel. So, I hope that you've learned many things for this chapter. So, thank you very much. Good day and stay safe.